Chef Boyardee, beef ravioli, gnocchi, and lasagna are made in massive automated factories with astonishing speed and scale. Wheat flour becomes soft dough, meats are ground and seasoned, and each dish is sealed and sterilized in minutes. In this video, we tour the full production line to see how classic Italian comfort food is engineered and canned for kitchens around the world. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reach the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf-stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, sauce pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day, with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning in place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year. A feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water, which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, Boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems, that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production: layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats: sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-size portions, the entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analysed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savoury but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the Nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotor-stator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees C over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. Excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat sealed along the underside, and crimp sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector, calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons, automatically erected from flat, blanks. Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 degrees C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, Steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Pre-formed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor aligned with the mold indexing system dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping infeed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with tool-less part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high-shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process. Sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coded one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second, over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent, followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0, 15 millimeters. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 millimeter. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle to print timing, is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree Kelvin. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, The hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees to create multiple flavor variants. The unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the weigh-filler interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk: sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees C. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film, printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece counting systems for final packaging. For bagged formats, vertical form-fill-seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored Nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, The spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 Celsius to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills 2 parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of 2 flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or pre-formed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high Brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. high-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 gralus of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +6 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Cs to 98 degrees Cs. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees Celsius. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. a high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate enrobing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry, where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider, where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust's structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, A mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrap sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station, where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. In the high-output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, can production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counter pressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for bricks levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine. Syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins, not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup to water ratio down to 0.1% so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, Every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins, not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading.